Today we are going to discuss collision. Here we'll discuss the types of collision like elastic collision, inelastic collision. Then we'll discuss elastic collision in one dimension, and after that we'll discuss elastic collision in two dimension. We'll also discuss how we get expression for the velocity after one dimensional elastic collision and what can be the different cases what we can get there. And finally, we'll discuss what is the coefficient of restitution and what is its use there. So all these we'll discuss in today's discussion. So let's take first of all the collision. Collision we are taking that this will be the interaction of one body with the other body. And here the collision we take it of two types. One is called as the elastic collision and other is called as your inelastic collision. So first one is your elastic collision and second one is your inelastic collision. First one, that is the elastic collision. It is the collision in which the linear momentum and kinetic energy both are conserved. So here linear momentum and kinetic energy both are conserved. But if you take inelastic collision, in this only linear momentum is conserved but not kinetic energy. In elastic collision both are conserved, but in inelastic collision it is only linear momentum which is conserved but not the kinetic energy. One question which is often asked, that for which type of collision law of conservation of energy is valid. So here we find that in elastic linear momentum and kinetic energy both is conserved, but in inelastic kinetic energy is not conserved. Here the students get confused that if the kinetic energy is not conserved, then probably conservation of energy will not be valid. Remember, law of conservation of energy is valid for both because it is a universal phenomena. Here what happens? Kinetic energy is not conserved simply means the mechanical energy is not conserved. This energy of law kinetic energy may get converted to some other form of the energy, maybe in the form of sound, maybe in the form of heat and other. But total energy, if you consider, it will always be conserved. However, mechanical energy will not get conserved in this inelastic collision. So remember, the law of conservation of energy is valid in both. But of course, in inelastic, this mechanical energy is not conserved. But the total energy, if you consider in taking different forms of energy, it will be always conserved in both. Let's take elastic collision in one dimension. Here we have two bodies, m1 and m2. m1 and m2 are the mass of the two bodies which are moving initially with the velocity u1 and u2 along the same straight line, and they suffer an elastic collision. And after the elastic collision, their velocities becomes v1 and v2. We want to find the expression for v1 and v2 in terms of the parameters which are given, that is your m1, u1, m2, u2, like that. So let's see how we can find velocity of the two bodies after one-dimensional elastic collision. We will apply conservation of linear momentum. So taking conservation of linear momentum what we find, initial momentum. That means momentum before collision. So m1 u1 plus m2 u2. This is your m1 v1 plus m2 v2. This is the momentum after collision, sum of the momentum. Or if you just simply transfer the terms, it is your m1 u1 minus v1. This is your m2 v2 minus u2. Let's call this as equation number 1. Now we apply conservation of kinetic energy. So applying conservation of kinetic energy. So now if you apply conservation of kinetic energy, what will happen? Half m1 u1 square plus half m2 u2 square. This is your half m1 v1 square, half m2 v2 square. This will be the expression. Or we can write m1, half will get cancelled from all these terms there. It is u1 square minus v1 square. This is m2 v2 square minus u2 square. This is suppose your second equation. Now we have to find the value of v1 and v2. So we need two equations there. These are the two equations there. Now what we do, for simplification, it will be easier if I divide this equation 2 by equation 1. Now dividing equation 2 by equation 1, this equation we are dividing by equation 1. So what we'll get here? u1 plus v1. This is your v2 plus u2. Because term like u1 minus v1 will get cancelled. Here also v2 minus u2 will get cancelled. Or you will get v2 equals to u1 plus v1 minus u2. Suppose I call this as equation number 3. Now we'll put this value of v2 in any of these equations. So obviously it is easier to put it in the equation number 1, because in that case if you are putting it in the equation 2, you will have to deal with the square term there. So here if we substitute it in the equation 1, so putting in equation 1, we have m1 u1 minus v1 equals to m2. For v2 we are putting this one, that is your u1 plus v1 minus u2 minus u2, because one u2 is already there. Or if you just transfer the terms there, suppose if I transfer m1 v1 this side, then you will have m1 plus m2 v1, and other will be your m1 minus m2 u1, this term, plus 2 times m2 u2. So m1 plus m2 v1 will be your m1 minus m2 u1 plus 2 times m2 u2. So v1, if I suppose right, it is your m1 minus m2 u1 plus 2 times m2 u2 divided by m1 plus m2. So this is the expression for v1. Now once we have got the expression for v1, that is the velocity of first body after collision, we can put that one in this equation and we can get the expression for v2. So putting it in equation 3, that is this one. So v2 will be equals to u1 minus u2 plus v1, which was there. So we are just substituting it, u1 minus u2 plus, for v1 it is your m1 minus m2 u1 plus 2 m2 u2 divided by m1 plus m2. And if you just simplify, it will be your m1 plus m2. We are taking LCM and then we are multiplying the terms. m1 minus m2 u1 plus 2 times m2 u2 divided by m1 plus m2. Now you can collect the terms of u1 at one place, u2 at other place. So if you collect the terms of U1, M1 plus M2 from here, and here this is the another one, M1 minus M2. This is your V1, or this is your U1. Then minus, this minus is there. So it is your M1 plus M2. And now this U2 term is there. So this will be minus 2 times M2 whole term multiplied by U2 divided by M1 plus M2. If you just simplify this one, basically the term like M2 will get cancelled. Here 1 M2 will get cancelled. And you will get here 2 M1 U1 plus minus M1 minus M2 U2 divided by M1 plus M2. So this is the expression for V2. This is the expression for velocity of second body after one-dimensional elastic collision. This is the expression for the velocity after one-dimensional elastic collision. What we have got for V1, we have this expression, and for V2, that means velocity of first body and second body after collision. We can take different cases here. Like suppose if I take case 1, we are taking if M1 equals to M2 equals to suppose M. So if you, that means you are taking the two bodies to have the same mass. So if you put it in equation 1, V1 will be how much? It is your M minus M. M1 and M2 both are equal. U1 plus 2 times MU2 divided by 2M. So that will give you, here this term will be 0. Here 2M will get cancelled. So you will get U2. So V1 will be equals to U2. And V2, if you put 2M U1 minus M U2 divided by 2M. So this time you will get it as U1. So what you get here? V1 is U2. That means velocity of first body after collision is same as the velocity of the second body before collision. And velocity of the second body after collision will be equal to velocity of first body before collision. That means what you can conclude, if two identical bodies are making one-dimensional elastic collision, after collision, their velocities will be simply exchanged. Let's take case 2. If we take M1 equals to M2 and we are taking U2 0, that means the two bodies are of same mass and the second body is at rest. So what you will get here? V1, which was your U2, because we have already taken M1, M2 equal in the previous case. So again here it is the same condition, only U2 we have taken 0. So this will be 0 and V2 will be your U1. It means if one body collides with an identical body at rest, then after elastic collision in one dimension, the first body will come to rest and second body will move with the velocity of first body before collision. So one body is colliding with an identical body at rest. So first body will come to rest after collision and the second one will move with the velocity of the first body. So this is your second case. Let's take case 3. If we assume that M1 is very large as compared to M2 and U2 is 0, that is the second body is at rest, first body has very large mass. So M1 plus M2 will be nearly equals to M1 and M1 minus M2 will also be nearly equals to M1. So if you substitute in the formula for V1, it is your M1 minus M2. So it is your M1 minus M2 U1 plus 2 M2 U2 by M1 plus M2. Let's just substitute it. m1 minus m2 will be nearly equals to m1 u1. Second body was at rest, u2 is 0, divided by m1 plus m2. So what will get? Nearly equals to u1. That means the first body will have almost the same velocity before collision. That means it will almost continue to move with the same velocity. What about v2? v2, if you consider, it was your 2 times m1 u1 minus m1 minus m2 u2 divided by m1 plus m2. So here it will be nearly equals to 2 times m1 u1, second term is 0, divided by m1. So this is nearly equals to 2 times u1. So v2 will be nearly equals to 2 times u1. That means second body, which is the lighter one, will move with double the velocity of the first body, whereas the first body will continue to move with its own velocity. So that means if a very large mass is colliding with a body of a smaller mass, much smaller mass at rest, then after collision, first body will continue moving with its own velocity, but the second one, that is the lighter one, which was initially at rest, will move with double the velocity of the first one. Let's now take a fourth case. If m1 is very small as compared to m2 and u2 is 0. So this time the first body has very small mass as compared to the other one, and the second one was at rest. So v1, if you consider, which was your m1 minus m2. Now here, of course, you can take that m1 plus m2 will be now nearly equals to m2. m1 minus m2 will be nearly equals to minus m2. v1 will be minus m2 u2 because it is your m1 minus m2, which m1 minus m2 is nearly equals to m2 into u1, and this will be equals to 0 because the second body is at rest. So now you will get v1 nearly equals to u1. Whereas v2, if you consider, it will be your 2 times m1 u1 minus 0 because u2 is 0 divided by m2. Now you see that since m1 by m2, we can write it here as u1, as m1 is very small as compared to m2. So m1 by m2 will be tending to 0. So v2 will be nearly equals to 0. That means if a lighter body collides with a much heavier body which is at rest, after elastic collision, the lighter body will be reflected back minus u1, whereas the heavier one will continue to be in the state of rest. So these are some cases which we can get in one-dimensional elastic collision. Let's take elastic collision in 2 dimensions, or you can call it also as the oblique collision there. Suppose we have m1 as the mass of the first body, which is moving with velocity u1. It collides with another body, that is m2, which is at rest. u2 we have taken it as 0. Now after elastic collision, the first body moves with a velocity v1 at an angle theta with, say, original direction or along x-axis, whereas the second body moves with a velocity v2 at an angle theta with the x-axis. You have to find, suppose, the velocity after collision, that is the elastic collision there. So here, applying conservation of linear momentum along x-axis. We are taking linear momentum along x-axis. So before collision, along x-axis, the first body has the momentum as m1 u1. Second body was at rest, so it will be 0. The velocity of the first body along x-axis, this will be equals to m1 v1 cos theta 1. This is the momentum of the first body along x-axis after collision. For the second body also, it will be m2 v2 cos theta 2. This is suppose your first equation. Similarly, if you take momentum conservation along y-axis. So what will happen? The first body, it was moving along x-axis, so it will not have any component along y-axis. So it will be 0. Second body was at rest, so its momentum is again 0. But for first body after collision, it is your m1 v1 sine theta 1. It will be in this direction, but for v2, if you take, it will be in the opposite direction. So it will be your minus m2 v2 sine theta 2. This is your second equation. So two equations we have got. Now for third equation, if you take applying conservation of kinetic energy. Remember, kinetic energy or the energy is a scalar quantity. So don't make a mistake of resolving that one along x-axis, y-axis. Momentum is vector quantity. So we can take momentum conservation along x-axis, along y-axis. But kinetic energy is a scalar quantity. So we can't have that component there in the different directions. It will have only one value there. So if you apply, then before collision, it is your half m1 u1 square. Second body will have the kinetic energy 0. This is equals to half m1 v1 square, half m2 v2 square. This is your third equation. So solving these three equations, you can find the unknowns there. Here you may say that there are four unknowns, v1, v2, theta 1, theta 2, and we are getting only three equations. So obviously we can't solve for all the unknowns. But in such cases there, or in such numericals or the problems there, any additional information will definitely be given. With that, you can frame fourth equation. It may be given that the two bodies after collision, they move mutually perpendicular. So you can take theta 1 plus theta 2 equals to pi by 2. So that will be the fourth equation. You can use it here. Or if it is said there that the first body has a velocity double the velocity of the second body. So again you have one relation between v1 and v2. So you'll get four equations there and you can solve it. There is one question now which is often asked. If a body collides with an identical body at rest, suffers an elastic collision, what is the angle between the velocity of the two bodies after collision? One body is colliding with an identical body at rest. After elastic collision, what is the angle between the velocity of the two bodies? Now here, there are two ways in which we can do. Suppose you have one body moving and this is the another body which is at rest. This is at rest, this is m and it is moving with velocity say u1. So here we know that if it is moving exactly along the same straight line or it is the collision in one dimension, then first body will come to rest after collision and second one will move with the velocity of the first one. So there the angle theta between v1 and v2 will be 0 degree. But if it is an oblique collision, like suppose you have this body and it is colliding with the another body, the center of the two is not along the same line. It is at some distance. So in that case, the bodies will move differently. So suppose the first body is moving with velocity v1 and the second one is moving with velocity v2. Let's assume that the first body, which was initially moving with velocity v, and this is the second one, that is 0. So for this one, we have to find what is this particular angle. If it is one-dimensional elastic collision there, in that case it is 0. But if it is an oblique collision, that means it will be the movement in two directions there. So in this particular case, by conservation of linear momentum, conservation, what you will get, mv vector equals to mv1 vector plus mv2 vector, or you will get v vector equals to v1 plus v2. This is suppose your equation 1. By conservation of kinetic energy, what we get, half m v square, half m v1 square plus half m v2 square. So you will get v square equals to v1 square plus v2 square. This is your second equation. Clear? Now what we do, we have vector v as v1 plus v2, so we take v dot v. It means it is your v1 plus v2 dot v1 plus v2. V dot v will be your v square. Angle between the two will be 0. So it is your v square cos 0. This will be your again v1 square, because it is your v1 dot v1. Then, or you can write in one more line there, v1 dot v1 plus v1 dot v2 plus v2 dot v1 plus v2 dot v2. Now you see v1 dot v1, how much it will be? v1 square. v1 dot v2, v2 dot v1. This will be 2 times v1 dot v2 plus v2 square. Now why? Because a dot b is same as b dot a. So we can take v1 dot v2 equals to v2 dot v1, and we can write it as 2 times. So this is your v square. Now if you compare this as the third equation, this is your second equation. So from second and third, if you compare, what will find? v1 square, v2 square will get cancelled, and you will get 2 times v1 dot v2 equals to 0. So it will give you v1 v2 cos theta 0, cos theta 0, or theta equals to pi by 2. So in this case, if it is an oblique collision, the angle between the velocity of the two bodies after collision will be 90 degree. If it is one dimensional, in that case it will be 0. Let's take now coefficient of restitution. Coefficient of restitution is the ratio of velocity of separation to velocity of approach. So it is the ratio of velocity of separation by velocity of approach divided by u1 minus u2. So coefficient of restitution we can write as minus v1 minus v2 divided by u1 minus u2. Why? Because v1 minus v2 will give you the velocity of separation, and u1 minus u2 will give you velocity of approach. From the value of coefficient of restitution, you can say whether the collision is perfectly elastic or perfectly inelastic, or it is inelastic. If I consider if E is 1, then the collision is called perfectly elastic. Okay, so if E is 1, coefficient of restitution is 1, then it is a perfectly elastic collision. What you will get here? Suppose you have a body and you assume that the body is colliding with a heavy, very large body at rest. Or say you take a ball, you drop it. If a ball is dropped, it collides with ground, it gets reflected back. So here we can assume u2 and v2 0, that is the velocity of the earth you can consider. So here you will get 1 equals to minus v1 by u1, because v2 and u2 will be equal. That indicates that v1 will be minus u1. And this is what we observe also. If a ball is dropped, it collides with particular velocity, suppose v. In that case, it gets reflected also with the same velocity. So this is what we get. Magnitude wise it will be same, direction will be opposite. If E is equals to 0, in that case we get perfectly inelastic collision. What we get here, E is 0, that means v1 minus v2 by u1 minus u2. This term is 0. That indicates v1 minus v2 is 0 or v1 equals to v2. That means after perfectly inelastic collision, the two bodies will move together. So what we'll get here, suppose there is one body, it is at rest, another body is moving with certain velocity, and after collision the two are moving together. They both move with particular velocity. So that will be the case of perfectly inelastic collision. You have a target. Suppose a wooden target is there and a gun is fired. The bullet gets embedded in the target, gets fixed there, and then the two moves together. So that is also a case of perfectly inelastic collision. So whenever the bodies stick together, in that case that will be the example of perfectly inelastic collision. So for any such problem or numerical, if you have to identify that what type of collision is there, in that case you can easily take help of this, the value of coefficient of restitution, and decide whether it is a perfectly elastic, perfectly inelastic or inelastic collision. In other collisions there, the value of E will be ranging there between 0 to 1. So this is all there in collision.